Hello again. So now we're looking at the estimate of the variance term. So the final model here, we're assuming the model has constant variance, and so the final parameter to be estimated is sigma squared. The variance of yi is the same as the variance of epsilon I, which is sigma squared. So we can estimate the sigma squared by the average of the residual squared. So in other words, if I take a look at, I'm sorry, this is all wrong. What I'm estimating sigma squared as is the sum from I equals 1 to n of ri squared, and I need to divide this by something. The thing I'm dividing here by is n minus k. Always what we divide by is the number of observations minus the number of parameters we estimated from data. So we reduce the degrees of freedom by that much. So here for simple linear regression, it's k is equal to 2, and we said before, that works out to be simply the mean sum square of the residuals. So s squared, my variance estimate here, is the mean sum square of the residuals, and from the table before, I have a table, this looks out to be 54.56. Once I have that, I can go further and actually try and work out the distribution for B1 here. So B1 here, we know looks like this, is SSXY over SSX. What I'll do is, the random term over here is yi, so I'll put in this whole thing, the bottom is a constant, this whole thing is ci. So my ci is, so my ci here, so if I add the ci, this is 1 upon SSX times the sum of xi minus x bar, and that's 0. If I look at ci times xi, then there's my ci 1 upon SSX, that's xi minus x bar times si. Now, that thing, the sum here is also SSX, so this is actually equal to 1. And finally, if I look at the squares, it's 1 over SSX squared times xi minus x bar squared. This again is just simply SSX, so one of the SSX's cancels off with the square. I get 1 over SSX. I'll use those results as I go through. The first of all, B1 is C1 times yi sum of. So the expected value of B1 is going to be C1 Ci times the expected value of yi. Ci is the constant. And the yi, because of the regression, is b0 plus beta1 xi. I separate this and I get b0 times the sum of ci plus b1 times the sum of xi times ci. This sum of ci is just 0, and the sum of ci xi is 1. So I'll get from here b1, beta1. So that means b1 is an unbiased estimator of beta1. On average, the value of b1 is equal to beta1. That's the mean. What about the variance? Well, if I look at the variance of b1, then it says it's ci squared times the variance of yi, and the variance of yi is sigma squared. So once I have that, what I'll get here is the sum of ci squares, and I know that the sum of ci squared is simply 1 over SSX. So just putting all this together, once I replace this by sigma squared, that comes outside the summation sign, and the sum of ci squared is simply 1 upon SSX. So because also the yi's are normally distributed, and b1 is just a linear combination of the y's, bi is also going to be normally distributed. So the mean is beta1, and the variance is sigma squared upon SSX. Or if I standardize that, I get b1 minus beta1 over sigma on the square root of SSX is normal not 1. Now, the problem is we don't often know sigma, and we estimate the thing by s. Once we have that, whenever I replace sigma by s, I get a t-distribution. And the t-distribution is going to agree with the degrees of freedom for my estimate of s, which is n minus k. In this case, is n minus 2. In general, that will be n minus k. And so this bottom term here, the s on SSX square root of, we call the standard error of beta1, of b1. Now, once I have that, I can perform hypothesis tests using the t-distribution, because I have a t-statistic over here to use. So for the Pharmax case, if I'm looking at the data as I have it here, all the information is available, if I want to test for a linear relationship, then my hypothesis is beta1 equals 0 versus the two-sided alternative. My t-statistic is going to be, well, I put the values in there, and I get the value is 6.304 as my t-statistic. The p-value, the two-sided p-value is twice probability t is bigger than 6.304. That's 8.59 times 10 to the negative 8. And if I think I have one of the numbers here wrong. Please go back a little while. I think I have this wrong, so this should be 8.59, I believe. Well, you can check that by using R yourself. So the p-value is much less than 0.05. So again, I will reject H0 and conclude there is a significant linear relationship. The one-sided p-value is simply going to be half of that, and I meant half there. The half of, sorry, it will be simply probability of t bigger than 6.304. That's half of what we had before, 4.29 times 10 to the negative 8. And again, the p-value is much smaller than the 0.025 or 2.5% significance level for a one-sided test. Same conclusion. But here we're looking at a strong positive relationship, and here it was just some relationship. Now, the one thing you'll notice is the p-value from the two tests is the same, whether you use t or the two-sided t-test or the f-test. And in fact, if you look at the observed value for the t-distribution, 6.304 squared gives you the f-value. In fact, it turns out that the tk distribution squared is the same as the f1k distribution. That needs to be a 1. And as we said before, the two-sided p-value and the one-sided p-value, and the one-sided is just half of the two-sided. Also, finally, we can also compute confidence intervals in the usual way. So I put 95% confidence limits for beta 1 will be b1 plus or minus the t statistic. T48 here is n minus 2, and n here was 50, so it's 50 minus 2. And my standard error for beta 1 or b1 was s on s6 square root of. Put all the numbers in there, and the t-value comes from tables or from R. You'll find the confidence interval for beta 1 comes to be that. Now the last part here will be model diagnostics, and we'll see that in the next lecture.